So the first scenario that we're going to start out with is a motion analysis, and we're assuming we have about 4,000 pound mass over our landing gear, and we're going to drop it with a 1G load, excuse me, from a few feet. So, not exactly a worst case landing load. And then we're going to take the stresses from that model and use those to calculate. We're going to take the loads from that model and use those to calculate the stresses in the parts. You see we have some nice tools in SOLIDWORKS to automatically go from motion to stress analysis. So we'll take a look at our finished model, and then I'll show you how we can build this model. We'll build a portion of it. So we actuate it just to drive it back and forth, and then we release one of our constraints and drop the model onto a rigid platform. So with the motion model, everything is assumed rigid. So we have a palette of tools to create relationships between our rigid bodies in the model. And what we can extract from this model are going to be forces at our different joint locations, forces at our contacts, and general dynamic behavior. For example, we can look at the contact forces on our tires, and we can look at forces between our joints or our linkages. So this is the sway link, which is the little blue link here in the back, and we're monitoring the force through that joint as we drop our mechanism. So my end goal for this simulation is going to be to take these simulation results and export those loads to a FEA analysis. So let's create a blank motion model just to show you some of the clicks. So we'll create a new motion study. And our mates from the SOLIDWORKS model are going to control the relationships between our different bodies. And we're going to turn on the motion analysis tab, which is the highest level of motion simulation. It's a full dynamic rigid body simulation. And we'll start out by turning on gravity, which is in our palette here at the bottom. And then we also have a time frame or a timeline showing what our different parts or forces are going to be doing in the model. So we'll select gravity and the appropriate direction. And we see it's going in the negative X direction. Now the palette turns colorful here with the calculation button because we have something to solve. Right now, there's not much to solve other than our landing gear is dropping like a rock. We do see that kinematic relationships between our parts have already been predefined with our motion mates. So now I can start using things like motors to begin constraining the model and adding forces. I'll choose a linear actuator, and I'm going to apply this to my mounts. So this is going to be holding on to my part until I say release this constraint and drop the part. So I will give this 0 velocity. Now when I solve the model, we're just swinging due to some offset loads and gravity. The next phase is we can start defining more motion behavior. So we saw that we cycled the actuator in and out during the first phase of the analysis just to create our pretty animation. That's also another motor constraint. So this time we're actually going to apply some motion rather than just holding the part fixed. I can pick the part that I want to apply the motion to, and I can reverse what's positive and negative. And I say I want the piston to move relative to the cylinder. And rather than a constant speed or a 0 velocity, I can define segments, which will give me a nice curve so I don't have to input points manually. So we're going to say at 1 second, we're going to extend to 6 inches, and then at 2 seconds, we'll go back to 0. And I'm going to run the analysis, I believe, for 10 seconds or so. There we go. So up to 6 and back down to 0. And motion models run quick, so I can stop and see what is it that I've done to the model. Okay, so we're actuating okay. The next phase is we might want to define some contact relationships between our tires and our landing pad or our tarmac. So I have a body down here, and if we scroll along our palette for the force elements, we'll see that there's contact. So what this is, it's rigid body contact, and we define a stiffness between our bodies, and we can pick groups or between all bodies in the select field. Instead, we're going to say that the 2 tire bodies are going to impact our tarmac, and we can pick materials to help define our contact stiffness. So I want this to be a relatively soft contact, so we'll just start with acrylic to acrylic. From here, we have forces that we can create, dampers, or springs. So we might want to create a spring and a damper relationship for our oleo strut here. So I'll go back to a section view so we can pick our edges and faces easily. And we pick the spring icon, and it's asking for the spring endpoints. So we can pick faces or edges. I'll pick 2 faces. And then from here, we can have linear and nonlinear springs. And we can define the length of the spring to create preload. And in this system, we do want to have a damper. And I will also go second order with my damper, nonlinear. And 10% of your stiffness is a good start point for your dynamic system. Now, in order to drop this model, I did use a tool called event-based motion. So we have a timeline view for our motion simulation. But in this case, I'm going to use the event-based motion to control my drop feature, the constraint that's holding the model in position. So we see here we can create a task, and it can be triggered by sensors in the model, such as position. But in this case, we're just going to use time, and say at 2.1 seconds after we're done actuating, I want you to take my drop motion, which is the motion constraint here on the mounts, and turn them off. So that's why when we animate this simulation, see the preload in the spring, expanding our linkage, and then the motion holding the system up is turned off at 2.1 seconds, and we drop. And then from here, we can start extracting forces from our model. In this particular case, I want to look at this link, and I've used the import motion loads to look at the worst case time to send the forces directly to the part so I can analyze it on its own very quickly and efficiently. And how did I pick my time step? Well, I looked at my contact forces and chose the highest forces, and that's the time step that I exported. We can also export multiple time steps. So we'll open this part,